So good morning, everyone. So we were at the topic of calorimetry. So we'll do some more numericals on calorimetry and then move on to a next subtopic, which is heat transfer by the process of conduction. So calorimetry. So let's look at some question. Calorimetry is fairly simple topic. In case of isolated system, the heat given is equal to heat gain is equal to heat loss. So let's look at some more application of the same. What is given here? A calorimeter contains 500 grams of water and 300 grams of ice at 0 degrees. So they are water and ice. They are in the state of thermal equilibrium. Okay, and a block of metal of mass 1000 gram is taken from the furnace where its temperature is 240 and it's dropped into calorimeter. As a result, all the ice is melted, but temperature remains at 0 degree. So this is one part. Okay, so this one part, and from this equation, what is the equation we can form here? In this case, this is if we start analyzing the first part here, heat transfer equation. Heat transfer here, this metal is losing heat energy, mc delta theta. And since the final temperature is 0, initial temperature is 240, 240 minus 0. And who has gained energy? Actually, there were three things in the system. First part, what is there in the system? There's water and there's ice here. And other side, this is something, this at the lower temperature, and other side is metal. So this one is losing heat and there it is gaining heat here. But since it is a 0 degree, what will happen? Initially, the temperature cannot rise. The temperature will rise only after it has converted into water at 0 degree. Initial amount of whatever heat is given to this system here, that will go into latent heat. So what has happened here? The entire ice has melted. So very easy, we can write the equation 300 grams of ice, which are 0 degree. So this is called latent heat. So it will gain heat energy in form of latent heat only. And this equation gives me what is the specific heat capacity of the metal. Now, next part of question, what was the final temperature of the system if mass of the block were twice as great? So very simple here. So in this case, what is the last sentence says? See, if we have water and ice, just visualize what is the case given here. There's a calorimeter here, and there's water here, and there's some ice also. And so when we drop a hot piece of metal here, actually calorimeter also is part of the system. But we ignored the heat capacity of the calorimeter. If not, so either mass of the calorimeter may be given, or as we have seen yesterday, is water equivalent also might be given. So this is fairly simple. And then when we double the mass here, very easy, heat transfer again equal final. So we assume here the final temperature to be T. Then see understand what will happen in the second case. Second case, what is happening? This metal now it has more heat energy. Is since the mass has become double, so when it cools down to so this has more energy here, so this also will go in more heat energy. When it goes more heat energy, initially first ice will get converted into water, then whole thing ice plus water, this put together, the mass of water will become 800 grams. So later on it will have sensible heat. So let's understand here, this is also pretty simple. Final temperature is T, mass has changed here, and this is what is this part here, this is mc delta theta for what? This is for water part. The water also will gain a heat energy, is it rises to temperature T, so T minus 0. And this is what the latent heat for ice, latent heat for ice. And then this is called sensible heat. Sensible heat is the part of heat which changes temperature. Now, very easy, we can write the equation. So, or I could have written here, this is the latent heat. After this 500 plus 300, it becomes a mass of water, 800 grams, and its temperature has been raised from 0 to T. So simple equation and we can get easily answer. Now look at some of the more cases here where see some cases we have mentioned here that even mechanical energy also can be converted in form of heat energy. So they are all equivalents. When you say one form is lost, it may get converted into heat energy. So this also example of something similar. The hailstone at 0 degree fall from a height of 1 kilometer on an insulating circuit. But you see, whenever mechanical energy gets converted, when mechanical energy is lost, it has to get converted in some or other form. So either in theoretically or as it mentioned in the question, so when it falls, when it hits the ground here, on this insulating circuit. What has happened here? In this case, if you visualize here, as it falling here, initially it is losing potential energy and gaining kinetic energy. So potential energy is getting converted to kinetic energy. And as soon as it hits the ground, the kinetic energy also is lost. And this kinetic energy has to go somewhere. Some part of it can also say it get transferred to surrounding air in form of sound. It gets air particles also start oscillating. So it may get transferred in various forms which are not easy to understand. But theoretically, we can say we cannot calculate. But yes, it can get converted in various form. What you're assuming here, this question it is given, entire kinetic energy gets converted into heat energy. If it gets converted to heat energy, since it is already at 0 degrees centigrade, what will happen to hailstone? If energy is not enough, first it will get converted partly into water. If height was even more, perhaps the entire hailstone may get converted into water. And if energy is even higher, not only it will get fully converted in water, the temperature also may rise, depending on kinetic energy. So kinetic energy is equal to, basically kinetic energy becomes equal to a delta Q. So all such question, and here it is given whole of it is converted. So delta Q is equal to 100% of kinetic energy. Sometimes the question they may also mention half the kinetic energy gets converted into heat energy. So whatever fraction is given, if it is given as 50%, I would have taken as 50%. So all such similar questions are conversion of mechanical energy into heat energy. And once we have heat energy, we can write as delta Q as heat energy. That's our understanding of heat energy. And this will lead to either ML. It will be, if it is like ice, or it could be MC delta T, or it could be combination. If it is in form of, like in this case, it would be combination of the two. Let's look at that. And what is important here, just note here, important part is units here. See, many times in units, we use CGS system, we use grams, calorie and all. So whenever we convert, we have to be consistent with unit. So let's see that one. Let's just pay attention to the units part. Let the mass of hailstone may be mkg. Mass is in kg. So unit also important. This topic, units also may vary. So it is implied that entire content is converted to this. So what is the heat energy received by hailstone is equal to mgh. So m into gh, so it will be equal to m into this is the energy. So we have assumed this is the amount of joules energy which will be given to hailstone. So when I am using joules here, I am equating here, since we have to find what part will melt. So this question itself indicates entire ice will not melt. Only part of it will melt. So we'll assume only x kg melts here. So where is this energy gone? This energy has gone into form of latent heat. It is melting x kg of ice. So delta Q will be equal to x into L. Since I have taken in joules also, I have to be careful. When I calculate, this entire term has to come in joules. So how do I do that? One is, of course, I can take X also in kg and latent heat also in SI unit. So here, if I have to take the latent heat I will take as 80 is the calorie. I convert into joules per kg. It becomes 80 into 4.2 into 10 to the power 3, so many joules per kg. And if I write the equation, X by M is the fraction of mass which gets melted. So what is the answer here? Fraction is x by x kg is melt out of total of m kg here. So that's a ratio what we needed. Had x quantity come more than m, what would it have implied? If height was much more, it is possible, if question was not clear, if x is more than m, it implies that it will melt and then temperature also will rise from 0 degree to higher value. Then we have to change the equation if it is x is coming more than m. Next one. So a thermally insulated vessel contains some water. So thermally insulated, this vessel here, and this is a little different type of question, vacuum. And vessel is connected to vacuum pump. So let's imagine what is there here. So there is a vessel here. And this is how it has to be airtight vessel. And you somehow might have noticed what the vacuum pump is. And there's some pump here, which takes the basically anything which is in the vapor form, vapor, it can take away vapor or it can take away air molecules. So it takes away this air, basically gas molecules from here. So thermally insulated vessel contains some ice, so it is not receiving heat, not transferring heat here. It contains some water at 0 degree centigrade. So there's water initially at 0 degree centigrade. Vessel is connected to vacuum pump, which pumps out air and water vapor. It is not pumping out water, it is pumping out water vapor. Okay, so that's what it pumps out. It is observed that when we use this pump here, slowly what we'll observe here, whatever water we had at 0 degree, it will start turning into ice. Okay, so what we have to ask, some water gets frozen, and we'll understand here why does it get frozen, and what is the maximum percent of water that can solidify in this way. So this is a little different kind of question, and let's understand how do we understand and how do we solve such question. See, vacuum pump converts, what will happen? So there's water here. The vacuum pump, when we first, before any of the water, if water doesn't get pumped out, it gets converted into water vapor first. Okay, so it gets converted in form of water vapor. So when it gets converted water vapor, basically it gains heat energy. And where does it get heat energy from? If water vapor, water has turned into water vapor, it has gained heat energy from other water molecules. It means within water molecule, within water mass, what is happening? Again, some kind of a distribution happening. Some of them are gaining heat energy. Some part is losing heat energy, and that is happening because of the pump. So when it gains energy, water gets converted into vapor, and the part which is already at 0 degree, so its temperature cannot drop. This converts into ice. So that's kind of redistribution is possible because of pump here. So assuming the fraction of original mass, so let's assume here what you are saying here. Okay. So fraction which gets vaporized, we are saying the so x fraction gets solidified. So if we have total 1, if x gets solidified, what will happen? Which part will remain in form of which part is vaporized? Remaining part is vaporized here. So out of 1 here, what has happened? Some part is turned into vapor. How much is the vapor part? 1 minus x fraction, and this is x fraction. So whatever, only now this is something, this is within the same mass, we have created this kind of energy separation. And when we write equation, what is heat transfer equation? Heat gained by part of water that vaporizes. So there's within this only there's heat gain and heat loss. Heat is gained by the water which is vaporized here, and 1 minus x is the part which is vaporized here out of 1, and heat of vaporization is given, latent heat of vaporization of water at 0 degree. Direct heat of vaporization is given, so I multiply by heat of vaporization. This is the heat gain. Heat lost by part of water that has solidified. It was lost in a heat energy which has made it to solidify. So this, if x part and x, what is the energy it has lost? It has lost energy equal to latent heat of freezing. 3 into 10 to the power 5. I get the fraction which gets solidified. So this is one of type of question. But one should know how to solve this one. And we get an answer here. And suppose this was not given directly, we could have written if this values were not given, this value directly. Latent heat of freezing of water, sorry, which is not given. So if heat of evaporation was not given, I would have written this one first. 1 minus x gram of water at 0 degree will convert into water at, but that is not appropriate. It will not convert to 100 degree. If it is not given, we need to assume that. I think leave that part here. Other part is something, one other variety of question you may come across where it is continuous process. So continuous process, something like this, just try to visualize here. What is the industrial process? Industrial process, this will happen in case of hotels and other places also, where it has centralized water heating system. So here 10 kg of water per hour is to be heated from 20 degree to 80 degree. You know, in hotels also we get hot water supply. So there will be some vessel which contains water and will get heated here. So industrial process, 10 kg of water, the number given are too small. Actually, it be much larger. But 10 kg of water is to be heated in 1 hour from 20 degree to 80 degree. And how is this done? This is done with the help of steam. So you have a boiler. What does boiler do? Boiler will heat up the water. It will turn into steam. It turns into steam. It is super saturated. This is superheated steam. So it is not 100 degree. It is 150 degree. And from boiler, it is passed through the tubes, and tubes are running through the container which has water to be heated. It runs through. So when it runs through, it has the coils here. So when steam runs through mass of water which is contained inside the vessel, it transfers heat to the water. Water gets heated up, and steam will lose energy. After passing through, steam comes out. So from other, there's an outlet here. So what goes in? It goes with higher thermal energy. It comes out with some loss of thermal energy. So steam will lose thermal energy, and accordingly, the water will gain thermal energy. That's what equation. And since it is a continuous process here, it is not a discrete mass. It is not mass defined in the boundary. So here heat transfer equation will take what time duration. The time duration is clearly mentioned 1 hour. Or we could have taken time t here. So let the steam which is passed from the boiler in 1 hour be x kg. So we could have also mentioned x kg of steam goes into the inlet in 1 hour, and it comes out here. How does the steam come? Steam condenses in the coil and return to the boiler at 90 degree. So what has happened here? Heat gained by part of water. So basically, water has gained heat energy. Enough information there to easily calculate what is the amount of heat energy water has gained. Water has from 20 degree to 80 degree MC delta T. So MC delta T, since I am using specific heat capacity in terms of calorie per gram per degree centigrade, because we are more comfortable with 1 calorie per gram per degree centigrade. So I'll convert the mass also in grams. So 10 kg. So this is mass in grams, M term. This is C term. Okay. And this is delta T, delta. It's 60 degrees change in temperature. So this is heat gained by part of water in 1 hour in terms of calorie. And this heat lost by steam will involve three parts. Three parts will involve. First, sensible heat. Sensible heat means part of the heat which changes temperature. So sensible heat first will cool down from steam at 150 degree to steam at 100 degree centigrade. And then after it steam 100 degrees centigrade, it will from 100 degrees steam at 100 degree, it will turn into water at 100 degrees centigrade. Then again sensible heat from water from 100 degrees centigrade to water at 90 degrees centigrade. So we have to add up all three parts here. And how much mass here? Mass is X, so I convert mass into grams, M. Okay, so first one is this one is C delta theta for the steam. Then this is L term here, and this term is again C delta theta. So if I have to use here, this C here is for steam. For steam also, the specific heat capacity is taken as 1. Only for ice it is 0.5, water is 1. So we substitute, we can easily find an answer. So this for continuous system also, we should be familiar with. So one more question I will do about loss of energy getting converted in form of heat energy. Well, pretty simple. Basically, what we get loss of whatever loss of mechanical energy takes place. This loss of mechanical energy, eh, some part of it gets converted into heat energy. So this is a so this is said some part of mechanical energy gets converted in form of heat energy, which can either change the phase or change the temperature. So any such question is something similar. Let's look at this 2 grams of bullet moving in certain velocity is brought to stop. It is entire kinetic energy is lost by an obstacle. And when the kinetic energy gets lost, it has to get converted in some other form. So in this case, what we are assuming here, again, we assume the total heat goes into, heat is absorbed by the bullet here. So entire heat, which are whatever the entire mechanical energy becomes heat energy, and this entire heat energy goes to whom? It entire energy goes to bullet here. So if the specific heat of bullet is so much, what is the rise in temperature of the bullet? So we have to just calculate delta T. So this question also is fairly simple. Entire mechanical energy is getting converted to heat energy. If the question was 50%, I would have multiplied kinetic energy into by 50%. So what is mechanical energy in terms of joules? Very easy, 1 by 2 mv square. We calculate, it comes into 40 joules. Only thing we need to be careful about units here. So if this is joule, basically delta Q and MC delta theta also we need to be either, this case I have done what? So here we are more comfortable MC delta theta. This comes in form of calorie. If I use mass in grams, if I use C as 1 calorie plus degree centigrade, this entire amount MC delta T, it is in form of calorie. So one way of what I'll do here, you can convert these joules also into calorie and then equate to MC delta theta. In that case, M has to be in terms of gram, C has to be in calorie plus gram per gram degree centigrade, and delta theta is also degree centigrade or or Kelvin. Both are same. So here we can convert, if it is 40 joules divided by 4.2, so many calorie, and I can equate the equation, I can find the answer. So need to be careful about conversion. We have to make sure both sides are in the same unit. That's all. And if I didn't want to convert, I would have written here also, this is equal to MC delta theta. In that case, I could have used M in kg. I would have converted mass into kg. In this case, especially this heat capacity also, I'll write as 4.2 kilojoules per kg. And that way also could have done. In that case, this MC delta T, if I substitute, right hand side also would have come in joules. So we have to make sure two sides are on the same unit. Right. So that is about calorimetry. Now we move on to heat transfer through process of conduction. Okay, so conduction, how do we visualize conduction? So if we have two heat reservoirs, and one is at higher temperature, other is lower temperature, across two heat reservoirs. So let's assume first we have heat reservoirs has constant temperature. So this side is maintained at constant higher temperature TH, other side has a lower temperature. So how do we maintain reservoir at constant temperature? Either we can heat, we can use a heater or something to make sure the temperature is maintained, or there are other ways also to maintain temperature. We'll quickly come to that also. So these temperatures are constant. So let's see whether we can just imagine any number also. Let's put it very easy to understand. This is 100 degrees centigrade and say it is 0 degrees centigrade. So how do we maintain constant temperature if in a chamber, if have steam at 100 degrees centigrade, what will happen? It will act as a constant heat temperature reservoir, because even if I take away some heat from here, initially the temperature will not change. When you take away heat from here, some part of the steam will condense, but it will still remain water, as it will become a mix of water and steam at 100 degrees centigrade. So whenever we have steam at 100 degrees centigrade, even if steam heat is removed, the temperature does not change. Similar way, and if it is ice at 0 degrees centigrade, if heat is given here also, it will turn a mix of ice and water at 0 degrees centigrade, temperature will not change. So whenever is something like this is there, it produces two heat reservoirs which are at constant temperature. Now let's say, so whichever way this 100 degree. So suppose I take a rod of metal and sides are insulated. So I take a metal rod and sides are insulated. You know, you have seen insulation. It could be thermocol or wool kind of thing. So insulated means it cannot heat, it will not lose from its sides. And this is connected around two reservoirs. So if before connection, if the temperature of the rod was, say, imaginary, say something, if the rod was 30 degree, entire rod, if it was in the room and room temperature was 30, so the entire rod was at 30 degree. As I connect across the heat reservoir, what will happen? This part, slowly the temperature will start rising here, and this part here nearer to the ice, this temperature will start falling, and similarly temperature will keep rising here, higher also. The temperature will keep falling. So what does it mean here? This part, right part here, it will receive some amount of net heat here, and this will lose some amount of net heat here within this. So this will happen. And if we leave it for certain time duration, what we find initially, though the temperature was uniform all across the length, and now the temperature will change and it will reach a steady state. So if temperature at two ends are remain constant, and how do we maintain the temperature constant? Either it's a large object here, it has large heat capacity. If it doesn't have a very large heat capacity, so even if some heat is removed, delta Q is equal to C delta T. If this value is very large, still if some heat is removed, the temperature will not change. So we have to understand what does large heat source mean. Large heat capacity means it has either very large value of mass. Typically, it will happen because there's a large mass here. Then change in temperature is negligible even when the heat is transferred, or phase change, as we discussed. That's how we provide heat reservoirs. After some time, we reach a steady state. How do I measure a steady state? See, visualize how do I measure a steady state. To measure a steady state, we could have done it. Suppose we put a thermometer at different points of the rod. So there are different thermometers. So what would I notice had we put the thermometer? Just when we place the rod, all thermometer would have shown the same reading, but this thermometer will start rising and this thermometer reading will start falling. What a steady state means, all thermometers, any number of thermometers are placed. After some time, I find the reading in thermometers is not changing. That's a steady state. The steady state, each part of the rod, it reaches a constant temperature. It does not vary with time. So steady state doesn't mean all parts have same temperature. So that means constant temperature has a different meaning. So that is not. Steady state means with time, temperature at any part is not changing. So it will reach, and if I look a point very close to this heater reservoir, here the temperature will be 100, and here temperature will be 0. As we move from here to here, we'll find the temperature will keep decreasing. So let's understand heat flow. In this case, even if the temperature has become constant, it doesn't mean the heat is not flowing. The temperature has become constant, still I find the heat will flow. If it is possible to see heat in motion, I could have seen the heat flowing from one end to the other end. But we cannot see heat flowing, we can see some other effect of heat flowing. If when it reaches the steady state, what I'll find here, if this was steam at 100 degree, I will find that steam will keep condensing. We'll find more and more of water at 100 degree. More this here, he will keep condensing, and here ice will keep melting. So if ice is melting progressively with time, even after it reaches steady state, it means it is receiving energy at a uniform rate of time, and this also losing heat energy. So and heat will flow. So and why is the heat flowing? Because of higher temperature to lower temperature, heat will flow along the shortest path. So in this case, this is the direction of heat flow. Direction of heat flow is along the axis of the rod, and in this case, I can call it x-axis. This is the direction in which the heat flow is taking place. So what other things are observations we can make about steady state? So typically we talk about steady state. So what are observation we can make about steady state? If I have a thermometer, if the rod is uniform, I'll find the temperature will drop uniformly along the length of the rod. So if I take equal distances, drop in temperature in equal lengths will be equal. And that's how the temperature. So midpoint temperature will be 50, one for the length from a temperature will be 75, here the temperature will be 25, so on and so on. Or if this is rod is 1 meter long, 100 centimeter, each centimeter temperature will keep dropping by 1 degree, which is called temperature gradient. So we'll have some observation. Let's see, they're all very simple points. Let's understand them at any point. So temperature at any point on rod, which is medium here, doesn't change with time. That's a steady state. So temperature is not changing. For uniform rod, the temperature gradient will be constant. So temperature also will vary uniformly. We'll see why that will happen. That also we can easily observe when this happens experiment. All particles on the rod on a section perpendicular to heat flow direction will have same temperature. So basically mean if I draw a line like this, what does this plane indicate? So this is like a plane here. This plane has x, a constant value of x. So since heat is flowing perpendicular to along x direction, in this plane, all points in a plane perpendicular to direction of heat flow, all points will have same temperature. That's what this particle means. Particle on the rod in a section perpendicular to heat flow direction will have same temperature. Heat flow rate is constant. So it means if I take different sections here, all sections, so I will just erase this part here, we'll move on to the next part here. So when heat flow is steady state, if I can somehow take a cross section here and measure how much heat has flown through, what is delta Q by delta T. In this section, everywhere I find the heat flow rate will be same. And there's reason why heat flow rate will be same in steady state. So heat flow rate is constant across any cross section. And reason is simple. If I take section 1 and if I take a section 2, so there is some part of medium material between these two sections. I can call this is a, so if I take this part of the rod or the medium, so if I imagine only this left hand side heat is entering and right side heat is leaving. So since this temperature is not changing, it means it's not receiving any heat. So amount of heat entering in a time interval should be equal to amount of heat flowing out. So heat flow rate will be similar to water flow rate. Water is flowing at a constant velocity through a pipe. You can visualize like that also. Heat flow rate is constant across any cross section. Hence, and what is the heat flow rate? Heat flow rate is depends on various parameters. What are the parameters? Heat flow rate is proportional to area. Means if I double the area here, heat flow rate, but basically doubling the area becomes two rod. So whatever heat one rod was carrying, the second rod also will carry the same amount of heat. Heat will become double. It also depends on difference in temperature inversely proportional to length. So basically this is a very simple formula, heat flow rate. I'm using expression x to denote heat flow rate, k into area of cross section. You understand, I hope you're all clear about area. Where, how do we measure the area? Area is the area perpendicular to direction of heat flow. So every time we need to know direction of heat flow, and direction of heat flow will be from higher temperature to lower temperature across the shortest path. And this and L is what is L dimension here? L is measured along the direction of heat flow. L is along the direction of heat flow, area is perpendicular. So this equation, and this equation is valid. I can apply between these two cross section. I can choose these two cross section to apply, or I can choose any two other cross section also to apply. So I can choose this is valid across any two cross section. So if I take one cross section like this, and if I take, where is this cross section? If I take this x is equal to 0, so I have taken one cross section at a distance x, and I have taken one more section here at a distance delta dx. Can I apply this formula across these two also? Yes, I can apply the formula here. Only thing, this becomes my tx, this becomes tx plus dx. I can apply the formula. Heat flow rate here also will be same. So in this case, what is the heat flow rate across the rod of length dx here? In that case, k, area is same, dt is the temperature difference, dx is the distance. The dx is measured along the direction of heat flow, area is perpendicular to heat flow. So these are the points what we need to understand for conduction. Rest all is very simple application of one formula. Only thing we can, this has similarity with water flow rate. So if you want to relate it to water flow rate, you can imagine this is a big water tank here. It's a large reservoir. So even the water flows also, water level does not change. There's another large tank here, which the water is at a lower level. So if we connect through a pipe, what will happen? As soon as we connect to the pipe, water will flow at a constant rate. So there we talk about volume flow rate or mass flow rate. That's what term we have used in case of liquid flow. Here we are talking about heat flow rate. Volume flow rate we can measure. Heat flow rate we can't see, but we can see its effect in terms of loss of heat here and gain of heat here. Right, so whatever amount of heat is lost in delta T, same amount of heat is gained here. Through the medium, there's no, basically, I hope you understand, every part temperature remain constant. So heat entering, heat leaving is same every breath. So I one more time when they said, so heat flow rate is constant across any cross section. Hence, we don't have to say what is the heat flow rate across any cross section. We can say what is the heat flow rate across the rod. Because across the rod, any section we take is same. Hence, we can use the term like heat flow rate through the rod. That's what heat flow rate means. It means through the rod means through any cross section of the rod, heat flow rate is H. Now, this term, what we have come across some of the times, since we deal with current electricity more often, we can use current electricity analogy. Heat flow rate, this is the term here. And here, heat is flowing, heat flow rate. There we talk about charge flow rate, so which is current is equal to I here. That is equal to V by R. So if we try to understand here, what is similarity? If I compare heat flow with charge flow, this is heat flow rate, this is charge flow rate. So this is delta Q by delta T, Q being the heat, here is equal to, yeah, this also charge by time here. And what is making heat flow possible? What is driving heat flow? Temperature difference. Here, what is driving current flow? Potential difference. So these two terms are similar here. So when we compare those two equations, this term is similar to voltage, and hence Ka by L is similar to 1 by R. So Ka by L can be taken as 1 by R, or resistance is analogous to L by Ka. So this we can call as thermal resistance. So we also use the term called thermal resistance, which is L by Ka. And for a small element, what would be thermal resistance if the length is very small? If something is varying, delta X by Ka also can be used as a thermal resistance for a small piece of conducting rod here. Okay, and what is the advantage here? So temperature difference causes the heat flow. So any problem in heat conduction can be converted into an equivalent current electricity problem, and sometimes much easier to solve with equivalent electric circuit having potential difference equal to Th minus TL. So this becomes higher potential, this becomes lower potential. So something like this is given. So this question also, what is the value here? So I can treat what is the potential at this point. Potential at this point is equal to TL, and potential at this point equal to Th, and resistance is equal to L by K. We can use that one. We will see some application of the same later. So that is when cross section of conducting medium is uniform. What happens if the conducting rod is having varying cross section? So something is things not uniform. There are number of ways it can vary. What are the ways it can vary? Is cross section may change, is conductivity may change. So any of those two things can vary. Conductivity may change at different position. It may have different conductivity, and it may have different cross section. So it is not uniform. Let's say two ends of conducting rod has a varying cross section. They are maintained at 200 degree and 0 degree. So this is maintained at 200 degree centigrade, and this is maintained at 0 degree centigrade. And it is varying cross section, but we also we can take as part of the rod here. We have taken AB and CD are two narrow cross section of the rod of equal thickness. So if whatever thickness this is there, this also thickness is same. So if this is equal to dx, this also is equal to dx. Only thing what will happen, this cross section and this cross section, we can easily notice here the cross section area is more, here cross section area is less. So let's see. So two cross section perpendicular direction of flow in a steady state. So it is given a steady state. So what we have discussed earlier here, any cross section heat flow rate is same. And I can apply that equation of heat flow rate across any section, any small element of the rod. So that when we apply that equation of heat flow rate, that has to be applied across any element of the rod. It must have some finite length. Okay, let's look at this. So in this case, temperature difference across. So there'll be some, of course, anything on the left hand side will have higher temperature compared to any section on the right hand side. So definitely here TA will be greater than TB. And here also TC will be greater than TD. Well, it's very simple to understand here. Only thing what you're asking is the temperature difference here will be equal or unequal. And if they're unequal, where the temperature difference will be more. So temperature difference on AD, AB, and CD. That's the question here. So let's understand what the temperature difference across elements of the rod will be temperature difference. So let's understand here, steady state implies unless stated. This is a very clearly stated steady state. So heat flow rate across all cross section is equal H. And if we take a slice of AB, then becomes a heat element. I can apply this formula. So heat flow rate, if I take AB also, heat entering is equal to heat leaving. Again, I'm repeating this point. So heat flow rate, any product will valid. This is the equation. If I apply the equation between which 2 points, if I apply this equation between this end and this end, this would be the equation. But this equation can be applied across any two cross section. So when I apply AB here, what this equation will be if I cross AB here, if I across this equation across AB, the equation H will remain same, K into area of AB. See, when these two, I am taking the slice width to be small. If area, this thickness is very small, I can assume the area at cross section A is equal to area cross section B, which is A, and which will be equal to delta TAB divided by dx. And so where this kind of term will come across. A similar way I can write across CD also. It will be K area across CD. C area can be taken as equal. This is temperature difference between C and D divided by dx. Both heat flow rates are same. If heat flow rates are same, we know the this area is greater. If this is greater than this, it means this term has to be smaller than other one. So temperature drop where area is more, the temperature gradient has to be smaller. Temperature gradient rate at which the temperature drops here. So temperature gradient will be smaller. That's the only point we need to understand here. And but the so if we have to draw a shape of temperature x graph, how would temperature vary? Previous case, it was a linear variation. So if the question comes, draw variation of, this is higher temperature. Higher temperature is with point at x is equal to 0, temperature is TH, and x is equal to S, temperature is TL. So between 2 points, the temperature will fall from here. What would the shape be? Will the shape be like this? Linear. If the rod was uniform, the temperature would have been linear. If it is non-linear, it could be something like this, or it could be something like this. So which is the correct shape? If I understand three shapes here, this indicates a temperature gradient dt by dx is equal to constant. Then only in the straight line. What does this curve indicate here? This curve indicates the slope is increasing. You understand, if you walk from here compared to this part, here the slope is increasing, or this curve indicates temperature gradient is increasing. Temperature gradient increasing. This indicates temperature gradient decreasing. As we move along x, the slope is decreasing. Slope indicates temperature gradient. Hence, temperature gradient is decreasing. So let's understand here what is happening here. If is the temperature, is this term here, this is the temperature gradient, is this temperature gradient decreasing with x or increasing? With x, area is decreasing, hence temperature gradient must increase. Slope of the curve must increase. Which slope is increasing? This slope is increasing. So this has to be the shape of which curve? Temperature x curve. This is the right shape. So I hope all are understood. Heat flow rate is same. With x, area decreases. If area decreases, temperature gradient must increase. If temperature gradient must increase, it means slope of this curve must increase with x. Magnitude. Of course, temperature is falling. We are talking about rate of change. Okay. Now coming to two rods connected in series. We can have multiple conductors also. It will not be same thing connected. So this we are connected steel rod and copper rod. And there's a furnace at 300 degrees and there's an ice box. So what will happen if you have furnace? So which is receiving? It's we are burning some oil and we burn in a controlled fashion so the temperature is maintained. So that becomes a heat source. And if we connect like this, depending on what the conductivity area and all of those things are, there's certain amount in a steady state, certain amount of heat flow rate will take place, and depending on heat flow rate, this ice will start melting. So in this, when they are connected in series, what is the important point here? In this case, heat flow rate across steel and heat flow rate across copper are equal. So something similar, heat flow rate is same, and when we talk about current electricity, we talk about I is equal. So when is I equal, which kind of connection is the current same? Series connection. So this also like a series connection. Heat flow rate is same and temperature drop of 300 degree is shared across those two. So it's very similar to the case. It is similar to resistance in series. The current is same and potential difference is shared. Potential difference shared in proportion of resistance. So where resistance is more, it means it need more potential drop for same amount of current to flow. Find the temperature at junction. So this also a common kind of question, and we can solve using current electricity analogy. If I have to solve with normal heat conduction, is very simple. Let the temperature of junction be T here. So in this case, I'll form two equations, one between this point and this point for first piece of rod, and second equation, this piece of rod, both cases H are equal. So I'll form two equations. So first part of the rod, K1, A1, whatever K1 area is given. So here the temperature drop is TH minus T. That's the temperature drop, length of the first part of conductor. Heat flow for the second part, K2 into A2, second part here. I am applying heat conduction equation between second part of the rod. So this will be T minus T low, lower temperature by L2. And when I equate those two, if all other terms are given, only thing unknown is temperature, we can find out. So that's a way to find temperature at the junction. And equating the heat flow rate can be found. Or we can also solve using like series circuit. We can also imagine like a series circuit, which we'll take up later in some example. Okay, let's take the example here. So two rods of copper and brass have same length and cross section. So this also LA, this also length is okay, lengths are equal here. and free end of copper rod is at 0 degree. So copper rod, there is joint section and there's a free end. Free end is at 0 degree, and free end of the brass rod is 100 degree. And it is in a steady state. Most cases will deal with the steady state. If thermal conductivity of copper is 4 times that of brass, let's understand what does that mean. If thermal conductivity of brass is K here, this is conductivity is 4K. It means it allows heat to flow much more freely. Copper is a very good conductor. Its conductivity 4 times. It means under identical condition, copper would have conducted heat at 4 times rate as the brass. So this, if I this is take as K, this is 4K. Find the temperature at the junction of two rods. This is a fairly simple question. I assume K and 4K, and similar to previous question, equating heat flow rate I can find. So that's the equation I could have written if I take this 100 and this temperature T, and I very easily can write this equation K and equal. So one case 4A per copper and brass, and I can find. Other thing what we'll understand here, heat flow rates are same. So when I write this equation, what is the equation here? Ka into temperature difference divided by length here. So what we understand here, area is same here. When I look at two parts here, right from here to here, if I look at here to here, K also is not changing. From this point to this point, temperature gradient will be constant. And from here to here, this slope will be constant. But these two are not equal. These two parts are not equal. So let's understand, if I plot temperature versus X curve, how would temperature and X curve will be here? So what is the slope here? So this slope here, since heat flow is constant, so product of K and temperature gradient will be constant. So when K is 1/4, slope will be 4 times. So this slope here, if I call this slope as M1 and this slope as M2, since K is 1/4 here, slope will be 4 times of this. So this slope will be 4 times as steep compared to this slope. And hence the temperature drop also here, temperature drop across brass will be equal to 4 times temperature drop across copper to have same heat flow rate. So if we understand here, very easily you can solve. This is 4 times. So total temperature difference of 100 degree will get shared in proportion of 1:4. So this temperature drop will be 20, and here to here it needs a temperature drop of 80. So temperature drop of 80 will make the same heat to flow. I can write this equation, otherwise also I can calculate. I could have done in form of equivalent current electricity circuit also. So if this resistance is R, if R is equal to L by 4Ka, this resistance becomes equal to 4R. So basically, if I assume one value, I take the smaller resistance R, and this resistance will be more because K is smaller. So if one is R, other is 4R, and this is 0 volt, this is 100 volts temperature. All I need to do, I need to find the potential here. So this is equivalent current electricity circuit. So here 100 potential difference will be shared in proportion of 4:1. So very easy, 4:1. This will be from this will become equal to 20 volts or 20 degrees centigrade. So we can solve voltage junction also. Let's look at some more question which have a cylinder of radius R. It's surrounded by cylindrical shell of inner radius R and outer radius 2R. So there's a core inside. This is a radius of R. So there's one material here shown in pinkish color, and this outer cylinder also. So this total radius, this radius is 2R. This is how they are paired. Now thermal conductivity of material of inner cylinder is K1. So this has thermal conductivity of K1, and outer cylinder has thermal conductivity of K2. Assuming no loss of heat, the effective thermal conductivity of the system is heat is flowing along the length of the cylinder. Which direction is the heat flow rate? Heat is flowing in this direction. If heat is flowing in this direction, what is the effective thermal conductivity? So this kind of question we have done in resistance in so many cases. I think we should be able to solve. So again, in this case, heat flow rate K delta theta by L, where area of the surface over temperature is constant. Now, so when we take area, another way to understand area over which the temperature is constant. Okay, so that's why it becomes perpendicular to surface. Another way to understand whichever direction it is flow, perpendicular direction flow from higher temperature to lower temperature along the shortest path. area of material conducting K1 is constant. If area of material conducting constant, heat flow rate across this internal rod. So is there any heat flow rate flowing across these two cross section? I think 1 minute. I think yeah. So if I draw a side view, the side view will be like this. This is inner core and this outer core. And if I am looking from this side, from lower temperature, I can see the heat flow is something like this. If I had to denote heat flow rate, heat will be flowing like this. Heat is flowing towards me if I'm looking for lower temperature side. Is there any heat flow across the boundary here? No heat flow will take place across the boundary. Heat flow rate is perpendicular to the cross section. So heat flow across inner core and outer core are independent of each other. I can calculate heat flow through inner part and outer part separately and add it up. So this is an example of rods connected in parallel. So in this case, both rods have same temperature difference, similar to resistance having same potential difference. So here also rods are connected across identical temperature difference. They are in parallel. If they are in parallel, as we say, the current is equal to sum of current through independent resistors. Here heat flow rate is sum of H1 plus H2. I can independently calculate H1 and H2. Heat flow rate through core is equal to K for that area, K1. Its area is pi r square. Temperature difference is delta theta by L. Similarly, at heat flow rate through the outer part here. Outer part is K2, not through core, through the annular part. And since the radius is 2r, area of the blue part here will be total area minus area of the inner part. It becomes 3 pi r square into delta theta by L. So what is the total heat flow rate? If we have to calculate equivalent conductivity, what does equivalent conductivity mean? Equivalent conductivity means heat flow rate should be same for same temperature difference and identical physical dimension. So if I have to replace with one cylinder having thermal conductivity K equivalent, and that equivalent cylinder should have same physical dimension. Length should be same and radius should be 2r. So cross section area and length are same. So what is the equation I write? So if it is equivalent, this is the equation I write. Equivalent with same physical dimension and same temperature difference. So if I equate, I get K equivalent, and very easily I can write an expression. What is K equivalent when they are connected in parallel? K equivalent is equal to K1 plus K. But this we can easily obtain this expression. You can easily obtain the expression. And I could have done it same in terms of current electricity also. In case of current electricity, it is equal to two resistors connected in parallel. How about two resistors are? What are R1 and R2 here? If R1, if I take core, is equal to L by Ka. It will be L by K1 into pi r square. Or I could have taken a radius. And what is R2 be equal to? L by K2 into 3 pi r square. And what is the equivalent resistance here? I could have taken equivalent resistance also as 1 by R1 plus R2, but I think compared to that, when you find parallel, this is easier method. So whenever they are connected in parallel, so we should understand what is parallel connection. Parallel connection, when heat flow through, each part is independent. They are connected across identical temperature difference. And the heat flow is sum. Look at some more questions which are also come in the examination, and let's understand so well so that any similar question we can solve. So this is rod, temperature difference of 120 degrees maintained across between two ends rod A and B. Total length is 2L. Total length 2L is given. This was the figure given in the examination. So if total length 2L is given, it means this was written as L by 2, this was given L by 2. So naturally this also was equal to L by 2. Okay, and this L by 4 was given, it means this part also is equal to L. So some part was missing, which is very easy to fill it out. So another bent rod PQ of same cross section is AB and length is 3L by 2. So this length becomes 3L by 2 is connected here. In the study state, what is the temperature difference between P and Q? That was a question which was there. We have to find what is the temperature difference between these two points. So this also was a very simple question. Let's see how do we solve such question. This kind of question, it's easier to solve using equivalent current electricity circuit. So how would I solve here? Everywhere, see what is resistance? When we take thermal resistance is equal to L by Ka. In this case, all parts everywhere, A is same. and K also is same. So simply in this case, resistance is proportional to length. So wherever we have the smallest piece, let me take the resistance of the smallest piece, that's R, and all other resistances I can write in multiple. So it means if resistance between AP is R, resistance between PQ, this part will be equal to 2R because the length is double. So resistance is proportional to L here because K and A are constant. So let the resistance of part of length L by 2 is equal to R. I can write resistance of all parts here. I need to write this part resistance, this part resistance, this part resistance, and this resistance here. And similar fashion. If I connect the circuit here, this becomes my equivalent circuit. This resistance is R. And sorry, I think one part is missing here. So this is R here. And this one length becomes equal to 3L by 2. Hence it is 3R, 2R, and R. And this potential difference is 120. I need to find potential difference between these 2 points. And this is electrical circuit. I think it's extremely easy to form. We replace with equivalent resistance 1.2 R. So what is potential difference across these 2 points here? We can easily find potential difference across two. So we can find current and then you can find VR, or we also know potential difference in case of series is proportional to resistance. So what would be my delta V here? Delta V will be in proportion of the resistance, that will be equal to 1 by 2R divided by total resistance 2R plus 1.2R into total potential difference. Total potential difference is 120. So this is like current electricity, and we can easily calculate. So whatever we get as potential difference is nothing but same as temperature difference. Voltage drop shared in proportion of resistance. So very easy question. I think could have been done about a minute's time, couple of minutes time max. Okay, some more questions here. 3 rods of the same material. Moment the same material, but the K is same. Having same cross section, A is also same. Has been joined as shown in the figure. So it is joined like this. And whenever it is given, we always assume sides are insulated. So no heat flow, heat is flowing across the length only. And each rod is same length. So length is same, cross section is same, material is same. It means their thermal resistance also are equal. This also is R, this also is R, and this also is R. If they were not equal, we could have written in terms of proportion also. So very easily could have written as multiple of R. We could have taken a smaller distance R, another thing we written in multiples, becomes very easy. And this is how the temperatures are maintained. We need to find temperature at the junction here. So temperature at the junction, and so we can solve. This is also fairly easy question. One way of solving would be a very common way of solving. Heat flow into junction is equal to heat flow out. There's no heat is retained here. So if this heat flow rate is H1 here, this flow rate is also H1 here. This flow rate will equal to 2H1 here. That's one way of solving this equation, which is nothing but basically, if you recall, is Kirchhoff junction rule. So equivalent to heat circuit, very easily I can write the equation. Or other way, what I noticed, this question is even simpler. This is 90 degree, this is 90 degree. It means 2 rods are connected in parallel here. I can replace with something like this. So this is R, and this is R. And this is 90 volts, this is 0 volts. I have to find voltage difference, very easy to find here. So this is very easy to solve this question when it is given like this. It becomes a little more tricky if this temperature is changed. What happens? This is say equal to 50 degrees centigrade. If it is 50 degrees centigrade, I can write H1 and H2, and this heat flow rate will be H1 plus H2. So I'll calculate H1, I'll calculate H2 in terms of temperature difference and heat resistance here, and from this equation, I get the value of temperature T. I'll assume the temperature to be T here, right? H1, H2. So what is the equation I would have written? What would H1 be in that case? H1 will equal to Ka into the temperature difference. If I'm assuming this as a heat flow direction, this temperature minus this temperature. So always the direction what I assume, accordingly the temperature, these two also have to written in similar fashion. So 90 minus T divided by L is H1. And similarly, I could have written H2 if it was 50. H2 would have been Ka into 50 minus T by L. And this heat flow rate H3 through third rod will have been Ka T minus 0 here. Well, this is something, this is the direction we are assuming. So tail end first and the head end later divided by L. And then I write the equation H3 is equal to H1 plus H2. So very easy. Any temperature also we can solve. Right. So this is what we have done so far, and I'll stop here for a small break, 10 minutes break. And again, we continue with conduction after the break.